Hi everybody, welcome back. So before we start our next part here, we just want to do a little experiment. I have one of these little transistor testers, and I have one of those KSC 922s, or KSA 922s in there. And if we look, our gain is 493, or HFE, and our VBE is 0.78. So remember that. We'll write that down. 393 and 0.78. Okay, now we're just going to do something a little bit different. I'm just going to take this and I'm going to hold it between my fingers, or in my hand, for a second. And then we're going to test it again. Look at that. Now it's up to 420 from 393. And our VBE has dropped to 0.76 from 0.78. And we don't know the third digit because this only can read to the hundredth of a volt. It can't read in millivolts. So now you can see one of the reasons that I don't like matching transistors on one of these things. And they all pretty much do the same thing. Okay, just using one of these really inexpensive eBay testers. And you can see once again, now this one's saying, this is the same transistor, and it's saying that the beta is 359. And it says that the VBE is 703 millivolts. And actually, this little cheap $20 tester can test the forward voltage drop across the base emitter junction to the third digit, whereas this one only checks it to the second digit. Now let's heat this up a little bit in our fingers again and see what happens. Just kind of keep the probes from falling off here. And let's test it again here. That should do it. And now it's up to, from 359, it's up to 413. And we can see that the VBE dropped from, what was it? 703 down to 650. So really, based on the temperature of the transistor and a lot of other things, these things can give you all kinds of crazy readings. So to just pick these up and stick them in the tester when you're trying to match transistors really doesn't work. Now again, how important is all of this? Well, it's only important with certain circuitry. A lot of circuitry is designed that VBE and that HFE is not super critical. There's a wide range that it'll work in. But when you're talking about like a differential pair or a long-tailed pair circuit or something like that, that does make a difference. And when you match transistors, you want to be able to match them accurately in the real world. So you can see which answer was right. When it was at room temperature or when it was between my fingers or something in between. Hard to tell. So the idea of matching transistors, you have to eliminate as many of the variables as possible. So that's one of the reasons that I use that little test jig over there that you see me use, and it's right here in amongst all the mess, just this silly little thing here. But you can see from the previous video that I did, the first video in this series on the Spec-1, that when you put the two transistors you're comparing into the test jig, you have to let them warm up and achieve a stabilized temperature to actually see how if they really and truly are matched or not. Doing it this way as you can see, has too many variables. So I just thought it'd be an interesting thing to show you and something for you to keep in mind. One other thing, let me see if I can find it even. I know I have one. So several people asked me about this one, and this is the kind of the upscale version of this one. So this is the 55, this is the 75, and this one, the main difference is that it has a USB connector, and you can actually connect this with some software to your computer, and there's some software that can do, well, I guess it can do some rudimentary curve tracing, and I'm not going to hook it up right now, but the bottom line is the curve tracing that this does is all at very, very, very low current, and really not real world realistic to what you would, especially on a larger power transistor. This cannot generate enough current and voltage to actually test a transistor where it needs to be tested. This one only uses a single AAA battery, and it does have a boost circuit, and when it plugs in, it'll actually increase the test voltage, I think somewhere around 15 volts or something like that. This one actually uses a, what is it, a type 23A 12 volt battery for the test voltage. So actually, if you're just running them on battery, this is probably a better one. But they both do the same thing. I mean, you can connect this on here like so. Some of you might not be interested in this stuff, but I am, and I know some of you are. So here's that same transistor again. And you can see it essentially gives you the same information, maybe a little bit more. A few other parameters that it'll give you, which is nice. But again, it's subject to the same issues that the rest of them are. So if you just want to check to make sure the transistor is working, and you just want to check the pin out, for instance, it's really nice to know. If you scroll around here enough, it'll tell you what pins go to, let's see, it'll tell you which pins or what leads are equal what pin. Yeah, red, green, and blue. Base, collector, emitter. So these are useful, but they're just not useful for transistor matching, in my opinion. And that's why I don't use them for that. Hope that helps. Now, of course, nothing beats an actual curve tracer, and with the curve tracer you can use real world voltages. You can see this one can go clear up to 500 volts, and you can put a lot of current onto the transistor. So you can put more of a real world scenario on there and actually look at the curves for each particular step. And for instance, this is 0.5 milliamp per step, but I mean, you can change this and test the transistor under more real world conditions. You can actually, there's a this one has a comparator where it can check both at once. You've seen that on other videos. And you can actually watch these expand and contract with temperature. So if I heat this up with my fingers, you see right here, you can kind of see that bottom trace starting to creep off the scale. You see that? And they're kind of getting wider and wider and wider. And then if you fan it, cool it off a little bit, just, you'll see this will shrink back down. And, you know, but again, you can let the two transistors reach equilibrium and match them properly. So just remember, transistors are a moving target. They can change based on temperature and other factors. So just using those little cheap testers isn't really a good way to actually do transistor matching. Alright, so we have these main filter capacitors pulled out, and if you recall, these were the ones that had to reform, and they were causing the fuses to pop till they got reformed. But now that they've been formed, and this thing's been running for a while, looking at the results, it's actually not bad. These capacitors are now looking pretty good. I mean, look at the dissipation factor and look at the ESR. And we're checking it at 1 kilohertz. Not bad at all. And here's a brand new PW series. And it's probably not going to check a whole lot better. Well, the dissipation factor is a little better. ESR is a little bit better. Yeah, it's better. Not by a whole lot, though. So, yeah, I mean, I have a feeling that those caps just had been sitting a long time and they just needed to reform, but the chemicals in the capacitors are still good. So these probably would be able to go back in and be reused, but I'm going to put new ones on because these are 40 years old and these are new, so we're going to put new ones in anyway for what they cost, and since we're already in there. So I'm in the midst of replacing these capacitors on this board, and a couple interesting things. All these white film capacitors you see here, these were originally non-polarized electrolytics. So you could see these, they have the BP written on them for bipolar. And they also had these large ones here, which are, let's see if I can find one for you. Where'd they go? Floating around in here someplace. There they are. These larger 33 microfarad, and you can see they're also non-polarized. And it just so happens that I had some of these Nichicon Muse series audio bipolar caps for that, and then I used the film ones for the 3.3 microfarad. So whenever I talk about low noise caps or the bipolar caps or whatever, anything that's 4.7 microfarads or below, so here's a set of 4.7s, and let me see, I don't know what I did with the old ones. Let me see if I can find them for you. Yeah, here they are. So these 4.7s right here, anytime you see these funny looking orange capacitors and they have the epoxy, let me see if it'll focus, the epoxy on the bottom, you see that, instead of the rubber plug, and they're bright shiny orange. And then these other ones also have the epoxy bottoms like that, and they're like a dull orange. Those are special low noise capacitors. You really don't want to replace those with a standard electrolytic. So anything 4.7 microfarad or below, I replace with these film capacitors. And you can buy these, you know, Mauser, DigiKey, all the normal haunts. These ones, I think, are made by Kemet, K-E-M-E-T. And you know, they're relatively inexpensive. They're more expensive than electrolytics, but they're relatively inexpensive. But if you look at this one, it's rated at 10 microfarads. And although you can replace them with the Nichicon FG, those gold series ones, the better match for these are special low noise capacitors for the audio path. The perfect match for these are these Nichicon KL series. You see them? They're like in a black case, made by Nichicon, and there's your 10 microfarads, 50 volts. And these are very good replacements. These are actually low noise, low leakage electrolytics, and they test almost like a film capacitor. They're really good quality capacitors. So that's what I use to replace. Anytime you see those orange capacitors, remember that those are low noise, those are special audio grade capacitors, and although you could replace them with like a standard cap, you really want to keep the low noise ones if you can. So just a little word there. All right, there we go. got it all recapped, and I think it's going to be good for a long time. So I cleaned all the controls, made sure those are good, and now I got to flip this back over and do the other board, and should be ready to do another test. Alright, so I have the filter amplifier all recapped, and before I put it together I'd like to show you something interesting. If you look at this relay, this is actually in the audio path. This is the muting circuit relay, so the audio from the whole preamp goes through these contacts. And if you notice, they're split, and there's actually two tiny little contacts on each one of these. So once again, these are bifurcated contacts on the relay. Now the difference between these types and the other types is there's two different kinds of bifurcated relays. This one is for small signal switching, and it actually has two identical contacts on each one, and they're both gold plated. So the idea is you get better surface area and better contact with the little contact pads with the split dual relay contacts rather than with one big single relay. They're gold, so they won't tarnish, and they have the lowest resistance of any of the metal contact materials. Now if you contrast that over here with these relays, these are the speaker select relays right here. I know there's a lot of reflection there and everything, I don't know, but if you notice on them, they're also bifurcated contacts, but if you notice, one is small and one is large. And the large one is going to be made out of tungsten. They're going to have tungsten impregnated contacts because they can handle very high current and very high heat. And this one is actually going to be either a silver or a gold contact, and they have very low resistance. So the idea is, if there's a high current situation, the bigger contacts with a little bit higher resistance will be able to handle that arc and so forth. Whereas this one here is actually designed to come in a little bit after this one and give you better contact area for less signal loss. So two different kinds of bifurcated contacts, and very application specific. So I just thought that'd be something interesting to look at. Alright, making some good progress here. I got the faceplate put on, and all of these screws were pretty badly corroded. I mean, you could see all the rust around them and everything. So I tried that thing where I just wire brushed them off and then heated them up with a torch and dropped them in some cooking oil, and it blackened them. I mean, it did blacken them again. They turned out really nice. So those are the 8 screws that go into the sides here that hold these handles on from the side. You can see the kind of screw holes on the side there. There's 8 of them. And then there's this whole bunch here, but I'm probably not going to do that to them. A, because I'm lazy, and B, because I'm lazy. So maybe I'll just replace them with other screws. Maybe I'll just leave them as is. I don't know yet. We'll see. So I need to put those back in. Spinning this thing around without hitting the camera and everything else, and my meter and whatnot. Got a nice funky looking cloth covered power cord, new one, and nice oxygen free copper. Well, I don't know if it's oxygen free, I'm just messing with you there. I don't really check my wires for oxygen. I don't know if they have oxygen in them or not. I do know that if I stick the wires up my nose, I can't breathe. So maybe that means that they don't have oxygen in them. But of course, maybe if I stick them up my nose and I can't breathe, it's because I breathed all the oxygen out of the wire, and then it has no oxygen. I don't know. Why don't you go on the comments down below and let me know if you guys have oxygen in your wires. I know the internet tells me that if I have oxygen in my wires, it makes my speakers and my patch cords sound bad. But I don't know. Tell me what you all think. Anyway, let's get this connected. We cleaned up all the connectors here, polished them, Tried to get as much of the crud off of there as we could. And I think this thing's generally ready to go. So let's get a signal source connected and get the scope connected and finish putting the knobs on and see how it works. Alright, we got the knobs on, we got the front panel put back on. I have a signal generator connected, the scope, the distortion meter, all that sort of stuff. So looking at this, at the specs a little bit, it says that our total harmonic distortion should be no more than 0.3% with 2 volts output. So let's check that right now, and I have it all set up already for you. And right there, let's see, with all the glare and everything, how's that? Get rid of the glare. So the first thing you want to check is, we can see we have 2 volts RMS output. That's what I have it set to, which equates to about 6 volts peak to peak. And if we go over to our distortion meter, yeah, 0.025, so that's just under 0.03. So this thing is meeting its specifications. Now, one thing I'll tell you, let's look at a couple things on this unit. These are very highly regarded, these Spec-1 preamps. I actually really like them. But from a specification standpoint, they're actually not as amazing compared to other units out there as you might think. This says that it has, for instance, the equalizer amplifier. That's your phono stage. It's a 3-stage direct coupled class A single-ended push-pull. And it says the first stage is a differential amplifier. So all they're talking about here, there's your differential amplifier. And this is what we replaced those 2 SA726s. This is why we used matched pairs. And then here's your second stage, which is kind of your driver for the push-pull output. And they say that it's a direct couple, right? So direct couple. What they mean by that is that the stages from here to here to here are direct coupled. You notice there's no capacitors from the output of this to the input of this and so forth. But if you notice, the input to the whole thing has a coupling capacitor and the output has a coupling capacitor. So even though this circuit is direct coupled, it is not direct coupled from here to over here, for instance, when you go into the tone amp or the filter amp. So all of the main assemblies are capacitively coupled. That's not a problem, though. I know a lot of people get really bent out of shape over capacitors in the audio path, but really, if you do it right, it's not a problem. It performs very well, as you can see from that. Again, the control amplifier is the same thing. And you look at some of the specs, like for the phono stage, I noticed that, where does it talk about the RIAA? Hold on a second, I'll find it. Here we go, right here. So you can see they're only measuring it from 30 Hertz to 15 kilohertz and guaranteeing plus or minus 0.2 dB. If you look at a lot of the higher end phono stages, they'll go all the way from 20 Hertz to 20 kilohertz and have that kind of a spec. So, and again, without actually testing this, we don't really know how well this is going to track from 20 to 20 kilohertz. That doesn't mean that this thing's limited at 15 kilohertz. It just means that it's flat, it has a flat response through that range. So not quite, definitely not like that Sansui AUX1 that we did the video on, or the Pioneer SA9800 or the 9100. Those were all really good phono stages. This one's good too. I just don't put it in the same class as those ones. But it should sound pretty good, and maybe we can do some improvements on this. I don't know. I'll have to look at the schematic and decide if it's worth my while or not, but we'll see. But really, all in all, this should be a really nice little preamp that's very solidly built and very very damage proof. And well, I guess the only thing left to do is just put it through a few paces here and just kind of see what it does. Okay, looking at the spec sheet here, it's saying at 2 volts output, we should get no more than 0.03% THD, and I have it set to 2 volts peak to peak. I believe that's how they're referring to it. And you can see right there, very low distortion. And if we take that up, let's see here. Okay. Let me move this down a little bit. And if we take it to 7 volts, because they're saying at 7 volts, and I'm going to have to trim that just a little bit. There we go. 7 volts peak to peak. We should get no more than 0.05%. And 0.03s, 0.029. So that's good. And they are talking about peak to peak. If you try to go 7 volts peak or 7 volts RMS, let's say, let's just try to see if it'll go to 7 volts RMS. I can almost guarantee you won't get that much output. See, it's starting to clip right now. So if we turn it just below clipping, about the most you're going to get RMS wise is about 3.5 volts RMS. That's a pretty strong drive signal, though, believe me, for driving a power amplifier. So there's plenty of output on this thing. And even at that high of a output drive, just under clipping, you can see it's still staying at 0.04. And they were saying at 7 volts peak to peak, it should be no more than 0.05. So it's way under its specs. It's running with these new capacitors and so forth. It is working pretty perfectly. So let's do a couple of other frequency tests here. All right, let's do our frequency sweep test and just kind of see if the amplitude stays flat. We're going from 10 hertz to 10 kilohertz, or to 20 kilohertz. So let's check that out. So we're going from 10 hertz to 20 kilohertz. And the idea is, if the amplifier is kind of transferring the signal flat, you shouldn't see the frequencies changing anywhere. And or the amplitude, I'm sorry, you shouldn't see the amplitude change throughout the frequency sweep. You can see it's staying pretty darn consistent. Now, just to show you what would happen if it did not, let me get the tone switch on, and for instance, I'm going to, there you go. So I took the 10 kilohertz treble control, and you can see what happens to the amplitude. And all I did was I turned the treble knob up a little bit on the 10 kilohertz treble control. So see, it starts out flat. The closer you get to that 10 kilohertz, the higher the amplitude hits, and then as you sweep through that amplitude and go back to the higher frequency, you can see right there, it'll sweep back down. See it? So watch, it's going to go up and then back down as you go higher in frequency. See, it drops a little bit and tails off. And then if we set our frequency controls to flat again, you can see it tracks flat. And same thing conversely, if we go to the bass control, we turn that up. As we go to high frequency, it stays pretty flat. But when it sweeps down into low frequency, see how it pops up over there real quick as it sweeps through that 100 hertz. So there you go. So anyway, the controls work just fine. Everything's good. And here's our volume, and you can see those stepped attenuators really make a big change. Okay, we ran into a little problem here, and I had to scratch my head for a minute to figure it out. So what was happening was, as you turned the volume up, I had to get clear past about to 1 o'clock before I really started hearing the volume get loud, and then all of a sudden it went really crazy the rest of the way. And at first I thought, well, what if they wired this attenuator backwards? You know, is there something wrong with the attenuator? And I had to really look at the schematics and think about it. And first of all, look at the block. If we look at the block diagram, here's what they're doing. You can see you come out of your buffer amplifier, which that comes out of your either the EQ, you know, the phono stage, or it comes directly in from your inputs, you know, auxiliary, tuner, and so forth. You can see straight in through the little buffer amplifier, which is, I believe this is unity gain. I'd have to look at the schematic, but here's what we want to pay attention to. Here's your volume pot, or your stepped attenuator. And by the way, on the old one, which there were some cracked wafers and things in it, it was in really, really bad condition when I looked at it. And you can see how worn this thing is, just terribly worn out. But when I looked at it, this is, in fact, a stepped attenuator. This is not a pot. In other words, that Alps pot that was in there is not a pot. See, these are little resistive elements, each one of these, and these are little switch elements. So it's actually a stepped attenuator, but it's not a normal one. It's a 4-gang. In other words, there's 4 of these inside that volume pot. However, 2 of them are wired the opposite of the other 2. I'll show you what I mean in a second. So when you look here, why do they have 4 volume controls if you only have a 2-channel stereo? Well, they're controlling the volume at the input of the whole preamp. In other words, where it's coming in from your input jacks or from your phono stage, it gets buffered through this buffer amp, and then your volume control is right here. So you're cutting the signal right as it's coming into the whole preamp circuit. But you're not just adjusting volume there, it's also adjusting the volume at the same time at the output of everything. So it goes through the tone amplifier and the filter amplifier, and then it goes to another volume control. So they're literally turning the volume up and down at both ends. The reason they're doing that is to reduce noise. They don't want to overdrive the input of this amplifier with this, and they don't want to have noise here by this having full gain all the time at the outputs. So, and then they have a buffer amplifier on each end to isolate it. Really neat design. But here's what's important. These schematics, or this block diagram, is not correct. If you look, those little dotted lines show you your clockwise rotation direction of the pot. This is the block diagram, but this is a typographical error. It's not correct. They're just showing you a kind of sequence of how everything works. But if you look on the real schematic, here's your 2 right and left channels, and they go up into your filter or your tone amplifier. But if you look, the dotted line on this side goes to the input, and the ground does not go to the dotted line. So you can see this one is wired differently. If you go to the other set of pots, which is down here at the bottom, you can see the dotted lines go to the side that goes to ground. So what that means is that 2 of the legs are swapped on one side and with respect to this other side. So what I had to do to make it correct, which the pinouts are all in line on the original Alps pot that they use, or stepped attenuator that they used in this thing. In other words, these wafers, there's 2 that are configured this way, and then there's 2 that are configured a mirror opposite of these. in order to make this work, I had to take these two wires of these two sections and swap them. So I had to swap this wire with this wire and this wire with this wire. These ones stayed the same as like the original layout of the pot. So this where it says input and output, that's a little bit confusing. Now that I've done that, it works absolutely perfectly, but what was happening is that it was switching in on one side, it was switching the resistors in the wrong sequence. We'll get more into how stepped attenuators work, because of course you have the ladder type, the shunt type, and the series type. I'll get more into that in another video. But suffice it to say, it works now. That's if you're going to use one of these standard stepped attenuators, and I would imagine one of those really expensive gold point would be wired just the same as this. Just know that these two wires, this white coax and this gray coax, you have to swap the input and output leads with respect to how they were on the original factory attenuator. So I hope that doesn't confuse you, but very important to know that. The other thing is on this, I had a couple people asking some questions about how these were put together. This adjusts the intensity of the detent. So the more there's a spring behind this, the more I screw this in, the harder the detents are going to be. So that's a really cool feature. The other thing is this has a set of screws on the back, and when you take those screws out, there's a little C-clip inside there that you take out, and then these wafers just pull apart. They're all gold-plated contacts, so I really doubt that, and they have insulating grease in them. They'll last a very long time. I don't think they're ever going to need cleaned anytime soon, and if they do, though, this can be disassembled to clean. So I just wanted to let you know that. Okay, let's get this put back together and continue on with our tests. Okay, we're all assembled now, and as you can see, I did not repaint the covers or anything, and I'm probably not going to until the weather breaks a little bit. I really don't want to go out in my shop and turn the heat on and all that stuff. It's really not going to hurt anything. I'm keeping this for me, so I can do this anytime when I'm ready, and I'll clean it up, or maybe I'll even just make a new cover for it. I don't know. We'll see. But inside, we know what it looks like. So now, to go off and do some more testing. So the first thing I'm going to do is I'm just going to look at, well, first of all, let's look at what we're going to use this with. I intend to use this preamp in conjunction with my Adcom GFA 585. And if you haven't seen that video series, it's pretty interesting. Check it out. I did a series where I completely rebuilt one of those, and it's the amp that I have down here in the basement. So I'm going to pair it up with this. So the first thing we need to know is, what is the input sensitivity of the GFA 585? Well, to get its full power output, it needs an input signal of about 2 volts RMS. So the maximum signal that I'm going to put into that amp to get full power, technically, is going to be 2 volts RMS, plus any peaks would go above that, but for a solid sine wave, according to the specifications, that's what we need. So I'm going to test this thing and see if it is capable of giving us a nice undistorted signal at 2 volts RMS and what it's going to look like. So I have the volume all the way up, tone controls are off, I'm feeding a 1 kilohertz signal into it, and it takes about 460 millivolts peak to peak. And I don't know what, I'd have to do the math to figure out what that is RMS, but essentially it doesn't take a whole lot of signal in to get that 2 volts RMS out. If we look up here, there's what we have, and you can see the two channels are right on top of one another. We have exactly, almost exactly, 2 volts RMS at our 1 kilohertz. And we are checking our total harmonic distortion, and you can see it's very, very low. It's 0.01 something, under 0.02%. Now, there are preamps that can exceed that by a huge amount, but this one's pretty good. And considering that, you know, you have to figure your test equipment, whatever distortion it has to begin with, the cables, any of the surrounding things that may add to the mix. So that's pretty good there. I had a viewer ask me about how I check THD with this Keithley, and I just want to show you something. Something maybe some of you know, some of you may not. So when you do the setup on this Keithley 2015, and most distortion meters will do this, so we can check either total harmonic distortion, or we can test synad, or THD plus noise. Okay, I leave it at THD because typically that's what all the spec sheets are rated at, is THD. Frequency Auto, this has the luxury of being able to track a fundamental frequency and pick it out as long as you're using a solid fundamental. Like I have a very pure 1 kilohertz sine wave, so it's pretty easy for the meter to pick up and say that the fundamental frequency is 1 kilohertz or whatever I feed into it. My upper harmonics. This tells you how many orders of harmonics you want to measure. Now, how much of a difference does this make? Well, when you're checking versus a sine wave, you really don't have to go past the second or third harmonic, because really it tapers off. Each harmonic higher that you get is going to be an order of magnitude lower in amplitude and going to have not a big, huge influence on your total harmonic distortion. So I go out 5 harmonics. So basically I have two odds and 2 evens. I have the second harmonic, I have the third harmonic, so that's the even and odd. Then I have the 4th harmonic and 5th harmonic, which is the second, even, and odd. So that's a big enough sample range to get a good idea of your total harmonic distortion. You can also check just the second harmonic if you want, and you'll see that cutting out the third harmonic will make a little bit of a difference, but not a huge difference. You can tell, and none of these things here, strangely enough, are really specified in a test procedure. If you try to go online and find this, you won't find much about it. You can learn about harmonics and all that, but as a test setup, you're going to have a hard time finding out what the test setup is that somebody's using. So just keep that in mind. Measurements and tests are only as good as the procedure that you're using. In other words, if you don't have every little detail documented as to how you did your test setup, it can't be 100% reproducible because you're introducing variables. So like things like the signal that you're feeding into it, the cables that you're using, the test equipment that you're using, the setup of the test equipment, all of those things will affect your measurements. So it's kind of subjective. When you see me do things on my videos and I show you different measurements and so forth, they're based on the setup that I use. And when you try to reproduce that on your bench, if you don't use the exact setup that I'm using, you could very well get different results than I'm getting, simply because your setup is different. So that's all learning test equipment. Maybe we'll do some more videos. I've done some videos on that, but maybe we can do more in the future. So units, percentage, you can also do it in dB. You can have a filter on there, and I do not have one in on this, and then it scrolls back around and there's your THD. So you can see that's actually a pretty good reading. You're not going to hear 0.02% total harmonic distortion. At least I'm not. Maybe some of you can, I don't know, but I can't. Just remember, whatever's there, that's going to get amplified. So there is some order of distortion in the preamp. So just expect to see that pass through to your power amp as well. And any distortion that your power amplifier adds to it is going to just increase your total harmonic distortion. But you can see this looks pretty clean there. All right. Okay, I'm not going to do a bunch of these, but I'm just going to show you some ranges. Let's go up to our 20 kilohertz. If I go to frequency and I go to 20 kilohertz, I'm going to leave everything else the same. I'm not going to change anything. I will change the horizontal sweep on the scope so we can see the sine wave, but everything else is staying the same. If we go down here, you notice our total harmonic distortion is actually a wee little bit lower, but essentially the same. It hasn't changed. So, and there's your sine wave, and you can see the output, this is really important, is still 2 volts RMS within 1/100 of a volt, or 10 millivolts. So the output of this, at least from 1 kilohertz to 20 kilohertz, is very, very flat. Now let's go down to a lower frequency. And this is the tough one, because remember, any amp that has capacitor coupling in it, if the capacitors are not the correct values and things, this is where you're really going to start seeing things. So if we go to 20 hertz, and we're not changing anything here, and I get a flat line. Why do I have a flat line, huh? I'm messing with you. Got to adjust the horizontal sweep again to fit this on the screen. And if we look, there's your 20 hertz. Right on, bang on, 2 volts RMS. And if we look at our total harmonic distortion, what happens here? You can see it starts to creep up a little bit. That 20 hertz is getting right at the edge of two things. Number one, of what this preamp can perform at without distorting the signal. And number two, you're getting to the edge of what my test equipment can measure. Measuring total harmonic distortion at frequencies of 20 hertz and below is very difficult for some of these types of test equipment. They are rated for low frequency, but you'll see as I go down, so let's go down to 15, there's 10. See, at 10 hertz, it can't even measure it. There's not enough, it can't measure that low of a frequency. If I go to, there's 15 hertz, it can't get it. 16, 17, 18, wait, here's it, 18, 19 hertz, right on the edge of measuring and not measuring. 20 hertz, there you go, it comes back. So you can't totally trust the THD meter at 20 hertz because you're right at the bottom of the band at which this thing can measure. If we go up to 30 hertz, you'll get a more realistic reading. There you go. There's 30 hertz. And you can see it distorts at low frequency a little bit more. It's actually flirting with 0.07%. As we get up to 40 and then 50, you can see it just keeps dropping off. 60, 70, and by 70 hertz, it's back down to really, really low. Again, some of that is the test equipment. So we can't really trust what this is reading at that really low frequency. We would have to look at the spectrum. So there you go, a little bit of how this works. I think what I'm going to do now is I'm just going to bring the amplifier here and put it on a bench and see if we can do some tests together with the amplifier to see how it looks. Well, I had to back the camera stand all the way back from the bench here to get it all in the shot, but here we go. We have the Spec-1 paired up with the GFA 585, and I have it connected through the speaker terminals. So as we saw inside there, you actually have speaker select relays that you can feed the output of the amp into the preamp and control the speakers between the A and B. Now this is not something you may want to do because of anything you put in the audio path can affect it, but as you'll see, it's not going to make that much difference, especially with those good contact relays that's in there. If you take a look, I have this set at speakers A. Now I have A connected up to the dummy load, and I have B set up to connected to an actual set of speakers, the clip speakers in the back there. And I have the auxiliary 1 connected to the signal generator and auxiliary 2 connected to the audio interface of my computer so we can play some music later on. So our first test, let's get up on the scope here, see if we can get some things lined up. There we go. And let me get the channels over top of one another. And I have a 1 kilohertz sine wave. And let's see what this thing can do. Remember, this is going to read our wattage. And here we go. It would help if we set our scope correctly. There we go. Okay. Bring this guy up. And let's adjust our balance. And right there is about 220 watts per channel. And we're not going to run that for too long, but there's your distortion. Not bad. So remember, this is about 250 watts per channel. But with this stepped attenuator, you can't get that analog adjustment. You know, you got to go between one of two steps. You know, it's kind of incremental. So you could see that's not bad. Now, once again, the specs for this amplifier are much lower than that. The specs for the preamp are lower than that. So you were seeing you were getting about 0.1, 0.15% THD. But remember, I'm reading how I'm reading with that meter, and you have to understand everything combines. So the distortion of the signal generator, the distortion by the cables themselves, and the distortion of the amplifier and the preamp all combine. So that's the distortion getting out to the dummy load through everything. When you think about that, that's pretty good for this system, especially being that I have this set up on the bench and just kind of haphazardly wired together. So I'm really pleased with that. Now, driving this at a much more reasonable 35 watts per channel, which is what you're going to be listening to when you're listening to it relatively loud volume, you can see our THD drops way down. Hi guys, you could see me. So this thing, again, looks pretty good. And let's see, we'll turn this up a little bit. If we kick to a square wave, you can see just the tiniest little bit of overshoot there, which is not a problem. And we'll look at slew rate here in a little bit. All right, expanding out on a square wave, we can see it's pretty square. No ringing or anything like that. And looking at the blue channel, we go, each one of these is, I have the times 10 divider on my dummy load, so each one of these square graticules is 20 volts. So we have 20, 40, 60, 80, 100, 120 volts right up here. And it's just about peaking out in 2 graticules, which is 4 microseconds per. So it's somewhere between 6 and 7 microseconds, and that's going to work out just around roughly almost 20 volts per microsecond, which is really good for the rise time on this amplifier. You got to remember, you're not just looking at the amplifier now. You're looking at the slew rate of the test equipment, the slew rate of the preamp, the slew rate of the capacitive couplers in the capacitive coupling in the preamp, and the slew rate of the amplifier all together, and we're still getting that out of it. Pretty amazing. So this combination is really performing well. So really the best way to tell how this thing works is to connect it up to a real set of speakers and an actual source for music. And of course, we're kind of limited by the goofy, non-copyrighted music. So let me go into my YouTube safe thing folder here, and I don't know. Let me find a song that's less annoying. And we'll play it. And I'm not gonna record this with the microphone or anything. You've heard me do that with this amp plenty of times when I did the amplifier video. We're just going to use the lapel microphone, but at least let you hear that, it sounds pretty good. Okay, so here's a song. I hope it's not too annoying. And remember, we're just going to use the lapel mic here, so no stereo recording or anything. And of course the washing machine in the background. I don't know how this microphone picks that up, but I can tell you that this is a very, this amplifier does not need a loudness contour switch, nor do you need the tone controls. It's definitely got a lot of low end, bottom end bass to it without any of that, which actually I kind of like it. It's pleasing to my ears. Some of the really mid-rangey, transparent amplifier and preamp combos that I listen to anymore because of my hearing now kind of give me a little bit of ear fatigue, because the higher frequencies don't sound as good to me anymore. Even if you turn them up loud enough that I can hear them, they kind of bother my ears a little bit, much more than they ever did in the past. And that's just a function of my hearing. As some of you younger folks get older, you'll see that your hearing will change as you age. And what sounds good right now may not sound so good then. But anyway, I really like the way this thing's performing. These two components play well together, very well. And I'm pretty happy with it. So, with the exception of eventually putting a new light in here and refinishing the cover, repainting it at some point in time, I'm going to call this one done. And it was a lot of fun doing this. Now, we may see this on the bench again, because I may decide down the road to do something unique with the phono stage, maybe. I don't know yet. And I may play around with, see if we can do a protect circuit, kind of integrate a protect circuit into these relays so that if there's any DC, remember these GFA 585s don't have any kind of protect relays or anything in them. And if this thing dead shorts, it can actually put a lot of power out to the speakers and trash them. That's one of the things you got to watch with these. It's pretty rare that it will happen, but I guess it is possible without having, sensing for DC on the speaker terminals. But that's it for right now. I think we're ready to move on to our next project, and this is going to go on my downstairs setup here in the basement and kind of be for listening and for testing things on. So ends another project, and I have another one ready to go already. And in the meantime, I want to wish you all peace, joy, happiness, and good health in your lives, especially good health in these times. I know I'm kind of dating this video, but I wish you all the best. And we're going to just keep working on this stuff and having a good time. And we hope to see you again real soon. So take care, everybody. And until next time, stay well. Bye-bye.